Welcome to CET2112C, Digital Systems 1. This video will be for describing and evaluating logic circuits. In this video, here are the things that we're going to cover. We're going to learn how to describe the truth table, the symbol, and the expression for the AND, OR, and NOT gates. We're going to describe logic circuits algebraically and be able to evaluate a combinational logic circuit output using a truth table. If you haven't already, you'll want to print the lecture notes that accompany this video and complete them with me as I go through the lecture. To begin, we're going to talk about Boolean constants and variables. When we talk about the realm of digital systems, it completely relies on the idea of Boolean algebra. And with Boolean algebra, variables can only ever be 0 or 1. So when we think about the inputs and the outputs to a digital circuit, those inputs and those outputs can only ever be 0 or 1. Also, we call those low and high. In the real world, if you needed to translate the idea of a 0 or a 1 to a tangible value or a tangible idea, a Boolean value of 0 corresponds to a voltage level from 0 volts to 0.8 volts. And we call this logic level low. So when we are building a digital circuit, if we were to ever take a voltmeter and measure the voltage at a particular input or a particular output, that voltage level is going to be considered a low or a 0 if I measure anything between 0 volts and 0.8 volts. Alternatively, a Boolean value of 1 corresponds to a voltage level from 2 volts to 5 volts. So if I were to measure an input or an output and I get a measurement anywhere in that range, I would consider that to be a high. Anything that doesn't fall within the range of low or high is considered to be an indeterminate range. It's neither a 0 or a 1, and it's technically an invalid state. We only ever want to be able to measure lows and highs or zeros and ones according to these voltage measurements. So, Boolean algebra only allows two values, 0 and 1. Some other terms that you may see for a 0 could be false, off, low, no, or an open switch. A logic 1 might also be considered to be true, on, high, yes, or a closed switch. So these terms are generally interchangeable, and depending on what realm of digital circuits or even computer programming that you're in, you'll see some of these terms. For example, true and false are generally used a lot in programming when you're evaluating the validity of a statement. So Boolean algebra is a means for expressing the relationship between a circuit's inputs and outputs when it applies to digital systems. The inputs are considered variables, just like you have seen variables in an algebra class prior to this. We consider the inputs variables, but those variables can only ever have an input level of 0 or 1. So if you take a look at the circuit on the screen, this is a basic combinational logic circuit. Notice we have three inputs, input A, input B, and input C. And those are labeled with variable names. And at any point in time, because this is a digital system and the only values that exist are 0 and 1, we know that the inputs for A, B, and C are only ever going to be 0 or 1. We know that the output coming out of this AND gate, the output coming out of this inverter can only ever be 0 or 1, and so forth. In a digital system, these are the only two options that we have. Either the input or the output is 0 or it's 1. And remember that 0 corresponds back to a voltage level between 0 and 0.8 volts, and a high corresponds back to any voltage level between 2 volts and 5 volts. So the nice thing about Boolean algebra compared to other types of algebra or other types of math in general, there are no fractions, no decimals, no negative numbers, no square roots, no cube roots, no logarithms, no imaginary numbers, and so on. When you only have two values, 0 and 1, the types of operations that you're going to perform are very different within the realm of Boolean algebra. So there are only three basic operations or three basic ideas that are involved in Boolean algebra: or, and not. So we're going to study these three basic functions and learn how they're implemented in a digital circuit. First, we're going to begin with the OR gate. This is our first Boolean operation. And for example, if you were designing an oven and you wanted the oven light to come on if the door opens or if the oven light switch is on, this is an example of where the idea of OR comes in. You want something to happen if one thing happens or another thing happens. Either one is fine or potentially both. That's the idea of OR. When we discuss the idea of OR, we begin with the truth table, and then we begin with a symbol to sort of represent what OR stands for. So first I'm going to start by looking at the truth table. The truth table is here on the left. A truth table is a tool that we use to be able to evaluate the output of any digital circuit. On the left, you're always going to list your inputs. An OR gate could have two inputs, and we're going to call those inputs A and B. So on the left, we have input A and input B. And then right below that, we have every possible combination of A and B. Now keep in mind, A and B can only ever be a 0 or a 1. So if those are our only two options for A and B, then we have four possible combinations. A and B could both be 0. A could be 0 while B is 1. A could be 1 while B is 0. Or they both could be 1. So when we have a truth table, the left side will always indicate the inputs and every possible combination of those input variables. On the right side of your truth table, you'll have the expected output based on the inputs. So for an OR gate, we can see that if both inputs are low, the output will be low. If the first input is low while the second input is high, the output will be high. If we reverse that and let the first input be high while the second input is low, we get a 1. And if they're both high, if both inputs are high, we get a 1. This is the concept of OR. An OR gate will always function in this way. Basically, we can describe this as an OR gate produces an output of 1 as long as at least one input is 1. So you will always get a high if at least one input is high. That's the idea of OR. And the OR gate is the physical digital circuit that we will use to implement this idea. So if you look at this symbol on the right, that's the symbol for an OR gate. Notice it's curved here, kind of like an arrow, and it has a point on the right-hand side. The OR gate will represent the ideas contained in this truth table. So if either one of these inputs are high, or if both of them are high, we will measure a high at the output. This is the symbol for OR. Now, this is an actual circuit that is designed to work in the way described based on the truth table. So what's inside of the OR gate is an actual digital circuit using a series of switches to create this output based on the truth table. You'll learn more about what's going on inside of the OR gate in your future classes. For now, it's important just to realize that anytime you see this symbol, it represents the idea of OR, and the idea of OR is that this gate will produce an output of 1 as long as at least one input is 1. And when we represent OR, we represent it with a plus symbol. So notice right here, right above the OR gate, we have X equals A plus B. X is just the variable name for the output of the OR gate. And then the A plus B represents OR in a mathematical representation. So in the realm of digital systems, I'm not going to really say X equals A plus B. Anytime I see a plus sign, I'm really going to say X equals A or B. The plus sign is like a symbol that represents the idea of OR. We're not physically adding two quantities together. This isn't like saying 1 plus 1 equals 2. We're saying that the output X is equal to A or B. And that word OR is going to represent this idea that we see in the truth table. An OR gate can have more than 2 inputs. It can have 3 inputs or 4 inputs or 18 inputs. It doesn't really matter. But the concept will always stay the same. So if you look at this picture here, we have a 3-input OR gate. So I have 3 inputs labeled A, B, and C going into the OR gate. My output is right here. Notice how it's written. X equals A or B or C. That's how we would read that out loud. We wouldn't actually say the word plus. Plus means OR. So this is our symbol for a 3-input OR gate. That's our output expression. This is the output expression right here. And then we have the truth table. I'm going to explain in a few minutes how we create the truth table when you have 3 inputs instead of 2. But for now, just take a look at the output. We can see that as long as any of these inputs are high, or if more than one input is high, the output will always be high. The only time the output of an OR gate will be low is if all of the inputs are low, which only happens right here in the first row. On your lecture notes, you have a diagram which shows a waveform. The waveform is a graphical representation of 2 inputs that are going into an OR gate at a certain point in time. And those inputs are changing. Notice that A starts out low, and at some point it goes high, at some point it goes low again, high again, low again, and so forth. What I want you to do on your notes is try to draw the waveform for the output of the OR gate. So what you're going to do is look at inputs A and B, and for each point or each period on the waveform, I want you to try to show the output. So take a minute right now, pause this video, and try to create the output waveform based on the inputs that you see here. All right, so now let's take a look at the solution to this waveform. So here's what the output would look like. It's shown here in red. Notice that whenever A and B are both low, the output is also low. And anytime that either A or B is high, the output is high. So we can see at these time points here, A is high while B is low. That'll give me a high. A and B are both high here. That'll give me a high here. A is low while B is high. That'll give me a high here. When they both go low, again, the output goes low. And then once again, the pattern repeats right here, where A is high while B is low. A and B are both high. And then A is low while B is high. So you're basically looking at the inputs and determining what the output should be based on those inputs. And in this case, this is what your output would look like based on these inputs if they were going into an OR gate. Let's do another example. Now we have a 3-input OR gate. So we have 3 input waveforms shown here on the left. In your notes, try to complete the waveform for the output of this OR gate based on the ideas we've discussed for a 3-input OR gate. Take a minute right now, hit pause, and try to figure that out on your own. Now let's take a look at the solution. If you have a 3-input OR gate, the idea is the same. The output will be high as long as at least one input is high. So you're just going to identify those places where that happens. We can see right here that A, B, and C all start out low. And then at this point, A is high. At this point, B is high. So from this point right here to this point right here, we know the output is going to be high because at least one input is high. We can see right here, all 3 inputs go low. Therefore, the output is low. And then we can see right here that input A is high. And it doesn't really matter what inputs B and C are doing at this point because as long as at least one input is high, the output will be high. And there's your solution. So that's the idea of OR. Now we're going to move on to AND gates. The second basic Boolean operation is AND. An example again with the clothes dryer. If you want the dryer to come on only when the timer is set above 0 and the door is closed, in this case, you want the dryer to come on when both things happen. It can't be one or the other. It must be both. That's the idea of AND. So here's the truth table and the symbol for AND. On the left, we'll start with the truth table. Once again, we're starting with the basic idea that the AND gate has 2 inputs. And those inputs are labeled as A and B. And here's our 4 possible combinations of those inputs. They're both low, one is low while one is high while the other is low, or they are both high. And the idea with AND is that you are not going to get a high at the output unless all of your inputs are high. That's the idea of AND. Another way to think about it is that the output of the AND gate is going to be low as long as any input is low. So if you have at least one input that is low, the output will be low. Or, again, you can think about it as all the outputs have to be high. All the inputs have to be high for the output to be high. Notice with the expression for the output right here, we use multiplication to represent and. So you can represent it the same way you would represent multiplication in an algebra class. You can use a dot like is shown here, or you can just put the two variables right next to each other to indicate that this is and. So if I were to read this expression out loud, I would not say x equals a times b. I would see the multiplication and say x equals a and b. Multiplication represents the idea of and. Just like with a 3-input OR circuit, we can have a 3-input AND circuit, and the idea of AND will extend to any number of inputs. So if I have 3 inputs to the AND gate, here's what my truth table would look like, where I have 8 possible input combinations between inputs A, B, and C. And then I can see that the output is labeled with multiplication, and I'd say that x equals A and B and C to describe the output. And then here's my truth table showing that the only time the output is high is when all 3 inputs are high. On your notes, you'll have another waveform for the AND gate. So take these 2 inputs that are applied to the AND gate and now try to determine the output waveform based on the idea of and. And here's the solution to that. Notice that the output will only be high when both of the inputs are high. And that only happens in 2 places. Right here, both of the inputs are high. And right here, both of the inputs are high. Anywhere else, you have at least one input that is low. So those are places where the output of the AND gate will also be low. Take a look at the next example for the AND gate and draw a waveform for this one. Keep in mind you have input A, which is constantly changing from a 0 to a 1, and then you have input B, which is high for some period of time and then goes low. What would the output of the AND gate look like for this particular set of inputs? Take a minute, pause the video, and try to do this yourself. And here's the solution for this particular problem. Notice that I can only have an output of high whenever both A and B are high, which happens 3 times. Basically, whenever A is high, inside of this section when B is also high. And that's what your waveform will look like for the output of the AND gate. Now, we've gone over AND and OR so far. Make sure that you know the difference in how they operate, as well as their symbols. The AND gate sort of looks like an uppercase D, or half of a Band-Aid, or I've heard it described as half of a skateboard. So however you need to think about it in your head, just remember that the AND gate has a flat edge here on the left and a very rounded edge on the right. Meanwhile, the OR gate is similar to an arrowhead where it's curved on the left edge and has a point on the right. Also, you'll need to always keep in mind the definition of and OR. The AND symbol tells you that the output will go high only when all the inputs are high. The OR symbol tells you that the output will go high when any input is high. And then the final basic Boolean operation is not. When the not operation is used, the output will be the inverse, the complement, or the opposite of the input. So here's the truth table that would describe that. If the input is low, the output becomes high. If the input is high, the output becomes low. That's the basic idea of not. And when we read it, or when we discuss it out loud, we could say a number of things. We could say that x equals not A, x equals the inverse of A, or x equals the complement of A. All of those are equivalent statements to describe the idea of the not gate. Not can be represented 2 ways, either by the overbar, which you'll see right here and in the diagram, or you can always use an apostrophe to represent the idea of not. The NOT gate is also called an inverter. And this is what the symbol for the NOT gate looks like. It's basically a triangle with a small circle on the right-hand side. You have to have the circle, so make sure that you always include that. It only has one input and one output. And whatever goes into the input will be inverted at the output. So if a 0 goes in, not 0 would come out. In a Boolean system, there's only two options, 0 or 1. So not 0 has to be 1, and not 1 has to be 0. So whatever goes in gets inverted. If a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. That's an inverter, or the NOT gate. So when we think about waveforms, the inverter will simply be a complement of what goes in, or sort of like a mirror image. Whenever the input is low, the output is high, and vice versa. Take a look at your example for the NOT gate and draw the waveform for its output, assuming that input B goes in. So again, an inverter is just going to give you a mirror image. Every 0 becomes a 1, every 1 becomes a 0. So you're just going to take each input and invert it to draw the output. And here's sort of a summary of and, or, and not. So when you have an or a 0 gives you a 0. And then as long as you have at least one input that's a 1, you'll get a 1. Keep in mind, this is not showing you addition. This is not saying 0 plus 0 equals 0. We're not doing a math problem the way you've done math in the past. This is Boolean algebra. What we're saying here is that 0 or 0 equals a 0. 0 or 1 equals a 1. 1 or 0 equals a 1. And 1 or 1 equals a 1. Remember, and is represented by multiplication, and then we have not represented with the overbar. So this is a summary of and, or, and not. Now we're going to move on to talking about truth tables. I've showed you a few already, but now we're going to practice building them and drawing them ourselves. We need a truth table to be the roadmap for any type of digital circuit that we're going to use. The roadmap tells us the inputs, every possible combination, and every single output that we would expect for that input. So for example, if this is the circuit I was building right here, the truth table would describe to me how I expect that circuit to work. So when I go into a lab and I actually build it, I'm going to test it and I'm going to make sure that it works according to my truth table. The truth table is the roadmap. It tells you what to expect when you build your circuit. It tells you what the output should be. And you'll use that as a tool to confirm that all of your circuits are working properly as you go throughout the semester. So we're going to talk about how to draw a truth table and how to complete one for any type of digital circuit you might see. So here are some example truth tables shown on the screen. Notice that if I have two inputs, I have 1, 2, 3, 4 rows. If I have 3 inputs, I have 8 rows. If I have 4 inputs, inputs A, B, C, and D, if I have 4 inputs, I have 16 rows. There is a relationship between the number of inputs and the number of rows. That relationship is 2 to the power of n, where n is the number of inputs. So if I have 2 inputs, 2 squared is 4. That's how many rows I need. If I have 3 inputs, 2 to the third power is 8. That's how many rows I need. If I have 4 inputs, 2 to the fourth power is 16. That's how many rows I need. So there's a relationship that you can always use to determine how large your truth table will become. Notice that as we add more inputs, the truth table gets larger. And it gets exponentially larger based on a 2 to the n, where n is the number of rows. Now, if you look at the inputs for these truth tables, you should also be able to see that it's counting in binary. 0, 1, 2, 3. This is 0, 1, 2, 3, 4, 5, 6, and 7. We've discussed earlier the binary number system, and as you learn how to convert very quickly between decimal and binary, you can easily see that the values in each one of these rows is just counting up from 0. However, there's also a pattern to it that you can use. If you start from the very last input, whatever is the far right input, the last input in line, if you start with that input, you'll start to see that there's a pattern. Look here at this input, 0, 1, 0, 1, 1, 0, 1, 1. Go to the next row, a column, and you'll see 2 zeros and then 2 ones. That's for a truth table with 4 rows. Let's look at a truth table with 8 rows. If you look at this truth table right here, go to the last input, which would be input C. Look again. The same pattern is beginning. 0, 1, 0, 1, 0, 1, 0, 1, all the way down. 1, 0, 1, 1. The next column has 2 zeros, 2 ones, 2 zeros, 2 ones. The next column has 4 zeros, 4 ones. So there's a pattern there you can always use to set up a truth table. When you create a truth table, the inputs will always look the same. So no matter what A, B, and C are connected to, if I have a 3-input circuit, the input section of my truth table will always look like this. It's the output that'll change depending on what the circuit is supposed to do. So when you set up a truth table, you're always going to set up the inputs the same way, either by counting in binary or by using this pattern. Take a look at if you have a 4-input truth table. The last input, 1, 0, 1, 1, 1, 0, 1, 1, all the way down. The next input, 2 zeros, 2 ones, 2 zeros, 2 ones, all the way down. The next input, 4 zeros, 4 ones, 4 zeros, 4 ones, all the way down. And then the final input, 8 zeros, 8 ones, all the way down. You can use this pattern to always set up a truth table, set up the inputs of a truth table. It will always work if you remember the pattern. So in the notes, I want you to practice drawing a truth table for a 3-input AND gate. You already know how the output is supposed to look because we've already discussed this, but I want you to practice physically drawing the truth table by hand. Make sure that you can set up a column for each input, a column for the output, and fill in the inputs as we discussed. So take a minute, pause the video, and try that out right now. When you're done, your truth table should start out like this. You have to have one column for each input and a column for the output. And then you're going to fill in each row, either using the pattern that we discussed or by counting in binary. 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, and so forth. So the input will look like this, no matter what kind of circuit it is. If it has 3 inputs, it will always look like that. Now we're going to fill in the outputs. Since it's an AND gate, we know that the output of an AND gate is only high when all the inputs are high. So your output column should look like that. And that's how you're going to draw a truth table for a 3-input AND gate. Now I want you to try to draw a truth table for a 4-input OR gate. And again, we already know what the output is going to look like because we already have discussed how OR works. But I want you to practice setting up the inputs by hand for that 4-input truth table. Keep in mind, if you have 4 inputs, that means you need 16 rows to show each possible combination of inputs. So take a second, pause the video, and try to draw the table for the 4-input OR gate. And here's what your input should look like. It should mimic the pattern that I discussed, or the fact that you're counting in binary from 0 all the way up to 1, 1, 1, 1, which is 15. Keep in mind that pattern was, again, 1, 0, 1, 1, 1, 0, 1, 1, all the way down. 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, 4 ones, and then 8 zeros, 8 ones. And since this is an OR gate, we know the output is going to be high as long as at least one input is high. Therefore, your output is going to look like this. Now we're going to move on to describing circuits algebraically, which is going to basically mean how do we write something that looks kind of like an algebra equation to represent the output of a circuit. So let's start with this first circuit right here. We have an AND gate with two inputs. The output of the AND gate is going into an OR gate with a third input. How would we write the expression for the output? That's the question. Well, you're going to go gate by gate and use the rules we discussed for and or not to do that. So let's explain this a little bit further. So the output here is going to be A and B. That's what comes out of this AND gate and then goes into the OR gate. So A and B goes into an OR gate with C. Remember, we represent AND with multiplication and OR with addition. So this is what the output would look like. Now, even though we're not doing algebra in this problem, order of operations still applies here the same way it does in a math class. In a math class, if we were to read this, we'd say that the output is A times B plus C. And we would do the multiplication before the addition because of the order of operations that we've learned. Same thing here, and comes before OR. So you don't necessarily need parentheses in this case because order of operations would tell us A and B first, then we OR that with C. But you could potentially use parentheses if you wanted to really drive home the idea that the multiplication came before the addition, the AND came before the OR. Let's look at another one. If we see the second example, the two gates are flipped. The OR gate comes first, and then the AND gate is second. So coming out of this OR gate would be A or B, and that entire thing goes into an AND gate with C. Here, it's very, very important to have the parentheses around the A or B. If not, order of operations would tell us that the B and the C would go into an AND gate first, but that's not what happened. The A and the B go into the OR gate first. So this is an example where parentheses are necessary because of order of operations, and you want to indicate that the OR came before the AND. Here, the parentheses don't really mean too much because of order of operations. Here, they absolutely mean the world because without that, you're not really writing an expression that adequately explains what's happening in this circuit. Let's take a look at the third one. We have an inverter here, so A is going to be inverted, and then it's going to go into an OR gate. The output here would be not A or B. Remember, you can write A with an overbar or a apostrophe. It doesn't matter. They both mean inversion. Keep in mind your apostrophe or your overbar should only go with whatever was inverted. So the overbar or the apostrophe is only over the A because the A is the only thing that went through the inverter. The B did not go through the inverter, therefore it should not have an apostrophe or an overbar. But look at the bottom example. This time, A and B go into an OR gate, and that comes out, and then that whole thing, that whole expression gets inverted. Here's an example where the bar has to go over the whole group. A or B went in, so that whole group, A or B, gets a long bar over the entire group. Do not put two small bars, one over A and one over B. That's not what happened. What happened is the group went into the inverter, so it gets inverted as a group. One long bar over the entire group. This is how we start to write output expressions. So now we're going to apply this idea to a more complicated circuit. This is a combinational logic circuit, which basically means it's just a combination of and, or, and not gates that are going to perform a certain function. Take a look at what you're given here. First, you have 4 inputs, A, B, C, and D. 4 inputs. So when you make the truth table for this circuit, you're going to need 2 to the 4, which is 16 rows, to capture all the possible input combinations. Now take a look at how the circuit is constructed. We can see that there's an inverter that goes into the AND gate and inverts input A. Inputs B and C also go into the AND gate. So what's coming out of this AND gate is not A, and B, and C. That's how we would write the expression just for that AND gate. Those three things are going in. They're being ANDed together, so we're going to write it with the multiplication for the expression, and it's going to be not A and B and C. That's how we would write what's coming out of the AND gate. Next, take a look at what's happening down here. Follow this line up and you'll see that it's connected to input A. Input A goes into the OR gate with D, and then the whole thing gets inverted. Notice I put parentheses around the group and then an apostrophe on the outside. That means the whole group gets inverted. That's another way to write the expression for inversion. The other way you would write this is to have a long overbar over the whole group. Either one of those is okay. So now if I look at the final AND gate, look at what's going in. A prime and B and C, and then A or D as a group inverted. Those are being ANDed together, so my final expression for the output would be this expression right here. That's the, again, output expression. So that's the first half of the problem. Determine the output expression. It's right here. And then we're going to generate a truth table so that we know how this circuit is going to operate for any possible combination of inputs. So again, your truth table should have 16 rows. And you're going to fill in the inputs exactly as we discussed previously using the pattern or by counting in binary. So you're going to start with inputs A, B, C, and D. You're going to fill in each input row by row using the pattern or counting in binary. Now, if you notice what I've put up here is one column to represent the output of each individual gate. The first column represents what's coming out of the inverter. The next column represents what's coming out of that AND gate. The next column represents what's coming out of this OR gate. The next column represents what's coming out of the inverter. And then the last column puts it all together for the final output. So let's start with what comes out of the first inverter right here. If A goes in, then not A comes out, which means every time I see a 0 in column A, it's going to become a 1. And every time I have a 1 in column A, it's going to become a 0. And that would be my output from that first inverter. Next, we have not A going into an AND gate with B and C. So think back to how we discussed an AND gate works. The output will only be high if all of the inputs are high. So in this case, we're looking for the time when B, C, and A prime are all high. That happens right here. And that's the only time it happens. If you look, A prime is 0 for the second half of the table, so we know we're never going to get a 1 out of this AND gate for these instances here. And if you look up here, there's one other time where they're all high, which is right here, the row right above. B is 1, C is 1, and A prime is 1. So we have two instances where they're all 1. Anywhere else, you have at least 1 0. Since we're thinking about an AND gate, we know that the output is only going to be high when all 3 of these inputs are high. And there's our expression and our output for the second AND gate, right here, the second gate. Let's move on to the third gate, which is this OR gate. Inputs A and D go into the OR gate. Remember that if at least one input is high, the output will be high. And I can look down here and see this large group of 1s for input A. So I can look at this huge group of 1s and say, I don't really care what input D is. I know that because input A is high, I'm going to have a 1 for the second half of the table, guaranteed. All of these here are going to be 1 just based on A alone. For the first half, the top half of the table, A is always 0, so then I'm only going to have a 1 whenever D is 1, which would be in these 4 places here, 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 here. And that's what my column for A or D would look like. Again, showing that if A is 1 or if D is 1, I'll have a 1 in the output. Next, I can see that the output of the OR gate becomes inverted, which means I'm going to take everything in this column and simply flip it. All the zeros become 1s, all the 1s become 0s. Last, I am going to have to do the AND operation. And I'm going to have to do an AND between not A and B and C, and A or D as a group inverted. So it's going to be very tricky sometimes to evaluate this looking at the table because you have to make sure you're looking at the right columns. Sometimes I like to draw myself a little arrow like this to remind myself what two columns I should be looking at. And then I'll often also write above that, what operation am I performing? According to my circuit, I'm doing an AND operation right here. So I need to look at this column because this is the first input to the AND gate. And I need to look at this column because this is the second input to my AND gate. And I'm going to go 0 and 1. 0 and 0. 0 and 1. All the way down, looking for the times when this column and this column are both 1. So if we look ahead, we can see that lost my highlighter for a second. Hold on. All right, so if we look ahead at this column here, we can see there's only two places where we have a 1. And if I go across to this column, there's only one place where they're both 1. Since these two inputs are going into an AND gate, I know that this right here is the only time when the output will be. Sorry, a little technical difficulty there. So as I was saying, the output is going to be high only when this column here and this column here are both high, which happens right here where you see this 1. So this is the truth table for this circuit. We can see there's only one time there's a 1. So what that means in a more tangible way is that if I were to build this circuit on the breadboard, and I were to connect A, B, C, and D to switches, and I could manipulate those switches to be either a 0 or a 1, depending on which row of the truth table I'm testing, I would see that the only time my output would be high, which would be your output would be connected to an LED, the only time your output would be high would be right here. This is the only time your LED is going to turn on your breadboard, on your circuit board. And that's when input A is 0, input B is 1, input C is 1, and input D is 0. Any other time, your light, your LED, will be off because the output is low. Flip the page in your notes, and I want you to try to do the truth table and the expression for this circuit on your own. Follow the same steps that we just did, and try to create the expression for the output and then the truth table for the output as well. So take a minute on your own and try this example. So with this example, we can see that A goes into an inverter and comes out, and that inverted A goes into the AND gate with input B. So the output of that AND gate we would describe as not A and B, or A with an apostrophe next to a B. We can see that input B right here is transferred to the AND gate. It's connected here, along with input C. So the output of this AND gate would be B and C. And then these two inputs go to the OR gate. So our expression, the output expression for this circuit would be not A and B, or B and C. And in this case, we don't really need any parentheses because according to order of operations, and comes before or, and we can see that as this is written, we would have and before or. Next, here's the truth table for this circuit. You only have 3 inputs, so you need 2 to the third, which is 8 rows. And again, you're going to set up those rows using the pattern that we discussed or by counting in binary. The inputs will always look the same way, no matter what the circuit is doing. If you have 3 inputs, your input section of your truth table will always look like this. If you have 4 inputs, the input section of your truth table will always look like the example prior. And then I gave you 1 column for each gate. So that means we're going to figure out the output of this inverter first, right here, then the output of this AND gate, then the output of this AND gate, and then we're going to put it all together to find the final output. So let's start with the inverter. If A goes in, not A comes out. So we take the zeros and invert them to be ones, and we take the ones and invert them to be zeros. Next, we can see that not A goes into the inverter with B. So I'm looking for any case in which not A and B are 1 at the same time, which happens in only 2 places. Right here. This is the only time they're both 1. Since this is an AND gate, that's the only time the output will be high. Next, we have inputs B and C going into an AND gate. So I'm going to look for all the times when both B and C are high. And I know that that's when the AND gate will be high. So B and C are both high here, and they're both high here. So I can see that the output is going to be high for those 2 rows. Everywhere else, the output will be low. And then, finally, for the last operation, I have to take this column and this column and perform OR based off of my circuit. So I'm looking at these 2 columns. I'm going to perform the OR operation to find the output, which means as long as at least one input is 1, the output will be 1. So the input is 1 here, they're both 1 here, and then an input is 1 here. And those are the 3 times that your output will be 1. Again, when we build this circuit, the ones in your truth table tell you that those are the times when your output should be high and based off of the inputs. So I have 3 cases where my inputs will give me a high at the output. That would be here, here, and here. So if input A is 0 while B is 1 and C is 0, the output will be high. Or if input A is low while B and C are high, the output will be high. Or if they're all high, if A, B, and C are all high, the output will be high. And I know that with any other combination, if I test any other one of these combinations in the table, the output will be low, which means I'll measure a low voltage between 0 to 0.8 volts, or I'll have an LED that is off. And finally, there's a third example in your notes. By now, I really want you to try to do this independently, so try to pause the video, create the expression and the truth table on your own, and then come back to the video and check to see if you were right. So with this circuit, we have A and B going into an OR gate. So the output of that OR gate would be A or B. Next, we have C, which is becoming inverted, going into an AND gate with D. So we'd have not C and D coming out of the AND gate. We now have those 2 inputs going to an OR gate. So we'd have A or B or not C and D. Remember again, order of operations applies, and we don't necessarily need parentheses in this case because AND would come before OR, and it does come before OR in the circuit. So we don't have to have parentheses, but if you added parentheses, it won't hurt. Lastly, this entire group gets inverted, which means our expression needs to have 1 long bar over the entire group, 1 long continuous bar, not 4 short bars. That's incorrect. 1 long bar. If the group goes in, the entire group gets inverted, the entire group gets 1 large bar. So that's the expression for your output. Next, here's the truth table. You have 4 inputs, so again, you're going to set it up the same way that we did in the first example using truth tables. Make sure that you follow the pattern that was described. This will never change. If you have 4 inputs, your input section should always follow this pattern no matter what. It's the output that'll change depending on what the circuit is supposed to do. And then you have 1 column for each gate. Here's the output of the OR gate, where A and B go into an OR gate. So as long as at least one of these is high, the output is high. Next, you have an inverter for input C. So I'm going to take the columns for input C and invert it. Instead of 2 zeros, 2 ones, I'm going to have 2 ones, 2 zeros all the way down. Next, I have not C going into an AND gate with D. So I'm going to be looking at column D and column not C and performing the AND operation. In other words, I'm looking for any times where both of these are 1. That is when the output will be a 1. So we can see that not C and D are 1 here. They're both 1 here. They're both 1 here. They're both 1 here. At any other time, at least one of those is 0. Since it's an AND gate, we know the output can only be high when both inputs are high. So we have 4 cases where both inputs are high. Next, we have A or B going into the OR gate with not C and D. So I'm going to be looking at these 2 columns, and I'm going to perform the OR operation on those 2 columns. So when I decide to fill in this truth table, the first thing that I'm going to do is sort of look ahead. I can see that in this column, I have a whole bunch of 1s. And this column is going into an OR gate. So I can use a little deductive reasoning and say, I don't even care about the other column. If this column has all these 1s right here, I know the output is always going to be 1 for the next column right here. All of these are going to be 1 because this column is 1, and it doesn't really matter what the other column is. So you can sort of look ahead to fill in when you have large gaps of 0s or 1s. So when I look at the output of the OR gate, the second OR gate, I can see that all of these 1s here dictate that the output will be 1 here. And then I really only have 4 rows to consider otherwise. Well, in these 4 rows, these are all 0s, so I'm not going to get a 1 from this column, but I am getting a 1 from right here. 0 or 1 is 1. So my final column is going to be an inversion of this one. Keep in mind, this expression gets inverted right here. So now I'm just going to take every 0 and every 1 and flip it. And that's going to be the expression for the output of this circuit. So again, the truth table is the roadmap. It explains every possible input scenario and what I expect as an output based off of those inputs. When you start building your digital circuits and testing them, you will always come back to testing it according to your truth table. And if your outputs on your circuit, when you build it on the bench, don't match your truth table, you know that there's something not right in the way you built your circuit, and you go back and fix it. So the truth table is a roadmap, and it's something that you'll have to be able to build and use as a tool as we go forward.